So good Monday afternoon, everyone. Welcome to lecture 15, Maths for Construction. Today we wanna, first let's recap what we did last week, lecture 14. We did APs, we spoke about what an arithmetic progression is, it's a sequence of numbers that follow a certain property where there's a common difference. The difference between the future term and the current term is the same as the difference between the current term and the previous term, right? It's not a good idea to say that in English, right? It's much better to use mathematics, okay? That's what this course is about. Human languages are imprecise and they're full of ambiguity, okay? Mathematics is the most precise language that we know of. That's why we learn it, so we could be precise as engineers when we specify in things, when we say in things, right? We need to have that precision in language. And only mathematics gives you that precision. We did some sample problems here with, the end term, some of the first sentence. We have some real cool homework here, these 5 questions. You should try these things. This will give you an idea where your skills are as well as what to expect, right? We start some basic trigonometry, science of triangles, right? We define the ratios here and we use the ratios to do some CSEC questions, right? Sum of angles and triangles, 180 degrees. General trigonometry is a little bit more interesting, and we will see that today because we want to move on to topics that use trigonometry inside of them. So you might think trigonometry is one topic, but it's there in several topics, right? So general trigonometry here, you ought to be given 3 things, and one of those things better be the size of a side, the length of a side in a triangle. If you're not given the length of any sides in a triangle, you can't figure anything out, right? We talk about Pythagoras' theorem. It's very useful sometimes, right? A lot of the times you don't really need it, but it's good to avoid thinking about angles. Sometimes it's useful, right? Like if I give you 2 sides in a triangle, you could find the other side if you know the angles, right? But if you don't know the angles, then you just have 2 sides. So Pythagoras' theorem could be used, but only if it's a right angle triangle. If it's not a right angle triangle, Pythagoras' theorem is replaced by the cosine rule, which we saw after in general trigonometry. This talk here is about inverses. What this means, sine to the power minus 1. It's not 1 over sine really, even though you might think it is. It's just the inverse, right? The sine function, given an angle, you could find the ratio, but sometimes we know the ratio and we want to find the angle. So that's why we use this notation here. You have different formulas for the area of a triangle. They tend to be useful, right? If you know one angle between 2 sides, you could find the area. If not, you had to use the other rules to find other things before you could find the area. General triangles, there's the sine rule and the cosine rule. Very, very important rules here. For you guys, this is all the trigonometry you really need to know. You solve a problem with it, use the sine rule. So this homework here, solve triangle ABC. Okay, I'll leave this for homework for you. I wouldn't do this now. Kind of want to move on and do new things, right? So let's look at our course outline. Course outline here. What we have, see, trigonometry, areas on volume, sine rule, cosine rule, area of triangles, right? So we do all of this last week, basically. Then you have this trigonometry here, which we'll get into, coordinate systems and inverses and so on. Areas and volumes are regular solids, right? Textbook has chapters on that. We know how to do these things here. Talk about matrices, we'll do that today. No stats so far. We did all the calculus. More trigonometry here. We had a one to talk about vector analysis. We already did the APs, right? This vector analysis here, say the word vector analysis. If you go any learning outcome, the only way you see vector analysis is in L4, right? It's here. Construction problem, vector analysis again. We already did APs last week. I'll do dimensional analysis towards the end of the course. So this thing about vectors, right? That's what I want to talk about. It says chapter 33 is where you need to study. So this is chapter 33 here. So as usual, you know, I'm not going to give you a note. You have a textbook. You just need to read it, right? We have things like scalar quantities. A scalar quantity is completely defined by a number, right? So like if, you know, somebody say, well, what is the mass of this object? And you say 12 grams. Mass is a scalar quantity. The values of mass, they have a magnitude alone, a number, right? The number is the magnitude. If somebody asks you, what is the temperature? You say 10 degrees Celsius, right? That's not a, that's what we call a scalar quantity. It's magnitude alone. Some quantities, though, not really a magnitude that's useful in either direction as well.
Yeah,
like
you
know, so if somebody asks you, you know, where is the plane headed, right? Give us the motion of the plane, direction of the plane. What was the speed and the direction? You say I would have a direction. It's not good to say, oh, the plane is heading at 500 miles an hour. They'll be like, well, where? West, north, east, where? Give us a bearing or something. Have a direction with that. So in engineering, we have quantities where it's not just the scalar quantity that's useful. It's not just a magnitude. It's a magnitude and a direction. And, you know, these are the popular things, quantities in engineering: force and velocity and moment and displacement, right? So, you know, these quantities have a magnitude and a direction. That's really what a vector quantity is. Now, the thing about vectors is that the rules of adding them is you add them algebraically, right? Or geometrically, okay? You don't just add them like an arithmetic, like 2 plus 4 is 6, right? 2 plus 4 in vectors is not 6. It could be anything, right? You're not sure. Because where's the 2, where's the direction of the 2, and where's the direction of the 4? They could cancel each other out to give 2, you know? Or -2, or you know, it depends on which direction you're taking as positive. So there are other complications with the arithmetic of vectors. The arithmetic of scalars is what the arithmetic we know, right? 5 apples cost $10. So 2 apples is 10 divided by 5 is multiplied by 2. That's $4, you know, that kind of thing. That's scalar arithmetic, normal multiplication. Like 5 by 3 is 50. Okay, for vector arithmetic, that's not the case. 5 by 3 is not 50. Okay, it's a different kind of arithmetic you have to know, you have to learn. And if I really trying to simplify it for you guys, vectors, the arithmetic of vectors is the arithmetic behind trigonometry, essentially, right? Vectors can be represented spatially as triangular, you know, triangle diagrams, right? A vector quantity is added to another vector quantity by using components, which you'll see in a while. So you see here like vector addition, right? Vectors are usually represented by a straight line with an arrow in the direction they're pointing to, and the length of the arrow is usually indication as the magnitude of the vector, right? So you see somebody say, okay, the speed of an object is 20 meters per second at an angle 45 degrees to the horizontal. That's magnitude and direction, okay? So for vectors, we have this bold print here, like A, B. First of all, you see is a direction is moving from A towards B. So the arrow is a dead giveaway is a vector quantity when you see something like A, B and an arrow on top, right? Here, if we want to represent this vector on a diagram, we could have units, right? Length of units. The arrow could be, if we say 1 centimeter represents 5 meters per second, then you know 4 centimeters represent 20, right? So the length of a line might be 4 centimeters, and you give somebody the scale 1 centimeter to 5 meters per second, and then you have to draw the line with a direction, and we have an origin, which is where the vector starts from, and vectors are to be given a name, say as lowercase a, and you also give it a position vector kind of notation here where it starts from E and it goes to B. So the arithmetic of vectors gets complicated fast, but essentially it's trigonometry underneath. For you guys at this level, 2-dimensional, 3-dimensional vectors is trigonometry. So if you don't know trigonometry, you can't do this stuff. That's why we did trigonometry last week. So sometimes you write a vector as a common letter with a bar on top it, or two capital letters on a bar. Sometimes we do instead of a bar, the line, the arrow from left to right. Sometimes you do it as underline letters, that kind of thing. I have several ways to represent a vector. If you want to represent it as a column vector, you know, this is like a column matrix, as they say. This is one column but 2 rows, right? So it's a 2-by-1 matrix here. The first coordinate, the first value is like the x coordinate from the origin, and the second value is the y coordinate from the origin. So this vector here, A34, has a horizontal x component of 3 and a vertical y component of 4. So we say column 3, 4. Right, like this. So we say 3i plus 4j. I is the direction of the x-axis. Y is the j is the direction of the y-axis. Right? So all this here is terminology, right? Vectors have magnitude and direction. So I'll be careful when you're telling somebody what the answer is if the answer is a vector. You can't just say 5. Like if I ask you what's the cost of 1 apple, you can't just say 5. 5 what? $5, 5 cents, 5 pounds, like 5 what we talking about, right? Even though cost is a scalar quantity. Same thing with vectors. You can't just tell somebody a number, you have to give them a number and a direction. Sometimes the direction is another number as well. Okay, sometimes it's just like a word as understood to be a certain thing. Like if I say this object speed is 5 meters per second north, that means it's facing north, it's heading towards north, right? So sometimes the direction is a number, is a quantity, and then you have a system of coordinates to understand that number, but sometimes it's just a word. So look at this problem here. A force of 4 newtons is included at an angle 45 degrees to a second force of 7 newtons. Both forces acting at a point. Find the magnitude of resultant of the 2 forces and the direction of the resultant respective 7 Newton force by triangular parallelogram. So you know you add vectors using geometry. So you end up with triangles and parallelograms and those kinds of shapes, right? So you have 2 vectors here. The 4 is at an angle of 45 degrees to the 7. We never say 7 is horizontal facing easter. We just say, you know, if this is 7, then the 4 Newton is at a 45 too. And we don't know if it's in this way or this way. And it don't matter because you're going to give the resultant with respect to the 7 Newton force. So again, the direction is with respect to the 7 Newton force. So you have 4 and 7 on an angle 45 degrees. So you have to draw a parallelogram, right? The resultant is the diagonal of the parallelogram. The 4 parallel to the 4, the 7 parallel to the 7. Diagram B here, this diagram here really shows you what's happening. You start from O, you go 7 across, and then you reach this point, say M, and you go from M up here at 4 in a direction of 45 degrees. So it's like you're walking and you're following directions. It's the same thing with the force, right? You have to follow a direction and a magnitude, because that is what a force is described by. It's not described by a single number. It's described by two numbers, the magnitude and the direction. So you're gonna, if you're adding two forces, you have to add them using the parallelogram law, as they say, or the triangle law. So here you see we have two triangles, a 7 and a 4 and 45 degrees. What's this angle between these triangles here, right? A straight line triangle is a straight line is 180 degrees. So if this is 45 degrees on the right here and the left is 135. So you have a triangle 135 degrees at this point here and a 7 and a 4. What will be the length of the diagonal? Where you use sine rule, cosine rule, what? You know two sides and the angle between them. Two sides and the angle between them. We did that last week. General trigonometry, two angles on a side or two sides on an angle. But if you look at the rules, when you know two sides and an angle between, you use cosine. So this is the technique you would use to solve a method like I use the cosine rule. So it depends on you knowing that rule. So you have nose to tail method. You put the 7 units along, you draw it horizontally, it don't matter, because you're gonna give the direction of the force relative to the 7. So 7 here, we draw horizontally. The 4 Newton force you draw relative to the 7 is 45 degrees. You see 45 degrees up here to the 7 Newton force. And the resultant vector is the length of that diagonal. Now you could draw it on graph paper, you know. Use a protractor and measure the lines, and you have a scale and so on. And you know, you could find your answer like that. Or you could just use, trigonometry, right? To find that value. So could we do that? Could we draw a triangle and solve that calculation? Let's see if we could try. So the question now, 4 Newton force is at an angle 45 degrees to a second force. Right? Both forces act on a point. So we could let that point could be C. So we have the 7 Newton force acting horizontally and the 4 Newton force acting at C, right? If we want to represent them as a triangle, we could have a line parallel to that AB line there. Let me see. That's now. So you try a different diagram here. Point C is where the two forces are acting, the 7 Newton and the 4 Newton. And they say the angle between them is 45 degrees. So that's the angle between the two forces here, 45 degrees. To add this, I draw the line BA, well, AB, parallel to that 4 Newton force, just to form a parallelogram. A parallelogram is a slanted rectangle, right? You have 7 below and the 4 on the sides. We had to add them vectorially, or algebraically, geometrically, right? You had to add these forces here using diagrams. This is how we add vectors. So the 4 and the 7 at an angle 45, that angle at B is 135. So I basically want to find that the length of this line B. And that line is opposite angle B, and I have these two sides here, 7 and 4, because of symmetry, right? This 4 on the left here is this 4 on the right, same direction, same angles. And the 7 below is the 7 on top. So I need to find AC. How you do that? Well, we need to use, we call this thing, we need to use cosine rule. Okay. So we come here now. We have two sides and the angle between them. So the two sides would be using these common letters, b squared, using the b squared formula. Right? So b squared is what we want to find. As you see, that's the magnitude of the resultant force. So you go 7 in this direction and 4 in this direction. So you go CB and then BE. So that will give you CE. To go from C to A, you go from C to B and B to A, right? So B squared is what? A squared what is A squared? Right, so the A squared, which is the 7 squared plus the 4 squared, minus 2 by 7 by 4 by, sorry, this is 135. 135 degrees, right? What is this equal to? Nine plus 16 minus this is what 56. So cosine 135 is minus root 2 over 2. So that minus root 2 over 2 multiplied by minus will give positive root 2 over 2. 56 over 2 is 20. So square root of all this here is 10.23, which is what they say here, 10.2 units young. But what is the angle? What is the angle ACB? All right, how will you find that? ACB. We could find ACB, or we could find, if we call this the point up here D, we could find ACD, and we could give the angle relative to the 4 Newton. What we want to give is easier to give the angle to the horizontal, which is the 7 Newton force. So what is angle ACB? We know a side B and the angle opposite is 135. So it looks like we're using sine rule for that. Right? So you can substitute into this thing here. A is what? A is 7, right? So this is 7. B is that 10.23. And C is 4. The other angle is 135 degrees. So the B is 135. We don't know ACB. We can't say A because the angle at A, the angle at A is this entire angle here. So we have to be careful. So 4 over ACB. And this is 7. So 4 over that is B over sine that is equal to CAB. So 7 over sine CAB. Right, so 7 over sine CAB is equal to 10.23 over sine 135 is over to 4 over sine ACB. So we just want to find ACB, so we're concentrating on these two here. So then we could cross multiply here. So you're not to find sine inverse of this here. Right. So the resultant of 4 and 7, 4 Newton and 7 Newton force is 10.23 newtons at an angle of 16 degrees to the 7 newtons force. Right? That's what the diagram is showing here. And that's what they said, 10.2 at an angle of 16 degrees to the 7 Newton force. Because we gave the answer relative to one of the forces that they give us, we don't really need to say north, west, east, or whatever. You need to give a direction, and that's the direction you give relative to one of the other forces. Right? Right? So 4 and 7, you might say, okay, I have a 4 Newton force and a 7 Newton force. You just add 4 and 7 and say, well, 4 plus 7 is 11. But 4 plus 7 is not 11 if 4 and 7 are vectors. If they act at an angle to each other, you have to take that angle in consideration. And then you use the parallelogram law or triangular geometry to add those links together. It's really links in a triangle diagram, right? Forces, all vectors can be represented as an arrow of a certain length with a certain direction. And the direction again is given at an angle to something else. So once you give your answer at an angle to some reference point, the answer is valid, right? Here in this question, we didn't have anything like north, south, or east or west. Similarly, here you have several forces acting together. You could use vector addition to represent it as a polygon, because now you have 2 more forces, right? Before you had 2, so you result in a triangle, but here you have several, 3. So you end up with a polygon, and you have to add this using geometry, triangles, right? So it gets a little bit tougher the more forces you have acting at a point, right? So one technique is your resolution of vectors. Given a vector and an angle to some direction, you could find the components, the horizontal and the vertical components. once you have the two components, you see here, we have a vertical component and a horizontal component. If F is a force and theta is the angle between the force and the horizontal, the vertical component is F sine theta and the horizontal component is F cos theta. So if you have two forces, F1 and F2, just add up the two vertical components to get the total vertical and add up the two horizontal to get the total horizontal. And then you use Pythagoras theorem to find the resultant. And then the angle between them, you use arctan. Okay. So you see here, if you have F1 and F2, H is this, right? And V is this. H is the total horizontal force, which is the other of the two horizontal components. And V is the two vertical components to give the vertical force. So you end up with one triangle like this here. H is this left to right, and V is the up and down. So from Pythagoras, H squared plus V squared is R squared, where R is the resultant. So R is the square root of the sum of squares of the two forces. And then if you look at the triangle, there's a triangle like this here, that theta is opposite over adjacent. Opposite is the vertical, and adjacent is the horizontal. So V over H is the tangent of the angle. So the angle is the arctan or the inverse tangent of V over H. So you see here this example, resolve an acceleration vector, which is 17 meters per second squared to the angle 120 to the horizontal. You draw a diagram, this is the diagram fit here. 120 degrees makes that acceleration component in the second quadrant, right? We count in an anti-clockwise way, first, second, third, fourth. So this is the second quadrant, this angle is 120 degrees. What's the vertical and what's the horizontal component? That's what I mean by resolve. When I say resolve into components, I mean take a vector and find the horizontal and vertical component. The horizontal component is negative because it acts to the left, right? Remember, to the right is positive and top is positive, so anything that acts bottom is negative. So the vertical component still acts upwards, but the horizontal component acts to the left. So you see again is a diagram. Vector diagrams are very geometric, okay? And you will see lots of triangles, angles, Pythagoras, all that kind of stuff, right? So you see here, they say find a resultant of two forces given in problem one. Right? Problem one, these are the two forces here. So you could use the components, right? Find the total horizontal component, which is that, the total vertical component, which is that, and just plug in everything into these formulas here, and you see you get back the same answer. So yet another way to solve the problem. So we could use the cosine rule, or we could use components, vertical and horizontal components to add vectors. You have two or more vectors and you have to add them. The idea is the same. You just find the horizontal and vertical components of all of them, add them up, and plug it into these formulas here. All right, Pythagoras will give you the resultant, and arctan will give you the angle to the horizontal. Okay, we say we used it to add the three velocities in problem two. See, problem two, we had three velocities here, right? V1, V2, and V3. So one was 7, one was 15, and one was 10. The 10 was at 20 degrees, the 7 was at 10 degrees, and the 15 was vertical. So if you find the horizontal and vertical components of each one, right? And then you add up all the horizontals, that's what this is here, right? This is the total horizontal. Then you add up all the vertical components to get the vertical component, and you just plug it into these formulas here to get the result. This is how we add vectors. Vectors are added using geometry. So parallelogram law, triangles, that kind of thing. You could look at the diagram and use a bunch of cosine and sine rules, or you could resolve into components and use these formulas here for the magnitude and the direction of the resultant, right? And then you have just problems, lots of problems to practice. So try this question here. We want to add two velocities, okay? So a practical example of this is you could be traveling at 7 meters per second at 115 degrees to the horizontal, right? But the breeze could be blowing at 3 meters per second, right? In this direction. So your motion combined with the motion of the wind will have a resultant motion, a different trajectory. Okay, so this is a practical application of that. So you could be going at this here, but the breeze going at this here, and both these forces or both these velocities acting at a point. So what is the resultant velocity, right? So use the diagram like what we did before. You could solve it using components, or you could solve it using, sine, cosine, or whatever, you want to use. You could try the components, right? But solve this problem. Take a couple of minutes, solve this problem, and we'll check it out when you finish. So what we could do, we could solve this using resolving vectors. So given these two vectors here, we could resolve them vertically or horizontally and horizontally, right? So there's a technique here in this last section. If you have two forces acting at a point, you resolve vertically, you call that V, you add up all the vectors, all the vertical components, call that V, and you add up all the horizontal components, and you call that H. So we must find the vertical components of each velocity. Okay, so we could, the book here they call them like F1 and F2, but we could call them U and V, right? We could use two letters, right? Let U equals the 3 meters per second. So we call this V. V is the 7 at 115. Okay, so U and V. So we find the components of U and V. So we'll say U. Let's do the vertical ones first, right? Okay, maybe those were not the best letters to choose, right? So we call them X and Y. X and Y. So X in the vertical direction equals the magnitude 3, and vertical is always sine. 3 sine 18 degrees. Okay, what is 3 sine 18 degrees? Lose all of that now. Right? Don't know what that is. So we do X and Y. Y is the 7, right? Horizontal is always cosine. Right? So the vertical components of each, we call them XV and YV, right? The X is 3 at 18 degrees. So what we could do, we could pretend that these forces operate at a point relative to the horizontal. So what we did here, I changed X and Y to A and B, okay? And to do this diagram here. So A is the 3 meters, right? Call this hold on, I think I make a mistake here again. It should be the 7. Right, so let me just change this up. Sorry for all this confusion here. Vector diagrams is really have to plan these things out, these diagrams, and name it better, right? So this should be B, right? So A should be the 7 at 115. B is the 3 at 18, right? Sorry for that confusion. So OB is the 3 and OA is the 7. The 7 is 115, that's what I give here. And the 3 is the 18, that's what I give here. Right. I don't know why this is happening. Right. So we have to find the vertical and horizontal components. So the vertical component of A is 7 sine 115. Vertical component of B is 3 sine 18 degrees as the vertical components. Horizontal components would be the cosines, right? What we do, we assume that both velocities act at the same point O, and angles are measured anti-clockwise about O, right? About the horizontal. So the horizontal line through O is this dotted line here. We are assuming that all angles are represented measuring anti-clockwise from the horizontal line. We could do these things because they want the answer relative to one of the components, right? So you see the direction of the velocities, we could give it relative to one of the components, right? Or we could say relative to the horizontal, right? We could decide what we measure in directions relative to. And that's the things with vectors. With vectors, you have to pick up a coordinate system, right? Something had to be naught, or something had to be 0, or something had to be like to the horizontal or to the vertical, okay? It's just very easy to solve this question, assuming everything is measured relative to the horizontal line passing through the origin. Okay, that's our coordinate system. So what was the value of all these things? 7 sine 115. How you find that? Seven multiplied by sine, oops. I think is how to do the other. 115 sine of that multiplied by 7 by 6.34. Right? Was 3 sine 18 degrees. 1/8 find the sine of that multiplied by 3 equals 0.927. Or 0.93. Seven cosine 115 degrees. 115 cosine multiplied by 7. Now you see this negative, 2.99. Negative 2.99 is what that looking like there. And 3 cosine 18 degrees. 118 cosine multiplied by 3 equals 2.85. Now, this negative component, we take in the horizontal right as positive, right? So you see this B here, we take into the right as positive. So 7 cosine of an angle less than 90 degrees is a positive thing. Once the angle crosses 90 degrees, cosine becomes negative. That's a property of the cosine curve. So what this means is the horizontal component, 7 cosine 115, is actually pointing left at a magnitude of 2.99. That 2.99 is pointing left. Because you see this A here, this A velocity is greater than 90 degrees. So it actually overshoots the vertical 90-degree angle and it pointing more to the left. So the component of this A vector here has a horizontal component pointing left. That's why it's saying negative here, because we take right as positive and up as positive, right? We take up as vertical positive and right as So up is vertical positive and right is horizontal positive. So when you see negative here for horizontal, it means it pointing left. So that component is almost 3 meters per second pointing left. The point is you don't need to visualize it totally, right? Just apply the formulas and work it out. But you have to have some geometrical sense of what's happening here. So there's these things here. The vertical forces is this AV and the BV, right? So the AV plus the BV as the total vertical things. This is the 6.34 plus the 0.93. Okay, what is that? Right. We could round to 3 decimal places if you want more precision, right? Horizontal now is these two guys here. So 2.99 yeah, let's subtract them and we keep the sign of the bigger number, which is negative 0.414, right? So this is pointing left. So there's a small horizontal component, but there's a vertical component upwards. So that means the resultant is a force a little bit to the left of the vertical 90 degree. There is a component pointing more to the left. It have no component pointing to the right. Okay, that because the total horizontal component is negative. So this means it's going left. So we apply the formulas here. The resultant is h squared plus v squared. This is very tiny, so the resultant could be almost 7, right? So R equals v squared plus h squared. That's what they say here, right? V squared, h squared plus v squared, same thing. What is this? So 7.27 squared right? So it don't matter if this is negative. So let me see. 7.27 squared plus 0.14 squared equals 5287.25, right? So that's square root 52.8745. No, 25. Right? Square root of this 7.27. So it's the same thing, almost the same thing, same 7.27. right? Same as the vertical component, because this is very small. There's a very small deviation left in the horizontal direction. So the angle will be very close to 90 degrees. Right? So tan inverse of V over H. Right? That's the angle. This is tan inverse of what? What over what? V is 7.27 and H is 0.14. This is a big value. This is a big number, right? 7 times 7 over 0.14. Let's see that. 7.27 divided by 0.14. Right, so it's 51.93. The inverse tangent, this is a little bit more than 90 degrees. Right, so second function, inverse tan of that is 88.9. Actually is negative, because this is negative 0.14. Sorry. So this is negative here. So it's a negative quotient. Right? Always remember that. So that's tan inverse on negative 51.93. So 51.93 minus 0 multiplied by so second function tan inverse of that now. $91.12. Right, so if I go and I say 91.12 and I find the tangent to that, it says negative 51 point something, right? So that angle 91.12 is a little over 90 degrees. And we see the answer here is very close to that with some minor rounding errors, right? But it don't matter. That is how you would do this using components. You resolve the components in both directions, vertical and horizontal, you add them up and you use the formula. Solving equations like this here might give you all some problems. I might have to teach you all that. Tan inverse of a negative value. What? Because the answer the calculator give you negative 88 degrees. That kind of don't make sense. Right? You gotta add 180 degrees to that. So that's when your syllabus they talk about up here for 4 quadrants. The different quadrants would have different signs and different values. So this is a set of theory here you had to learn about when an angle is positive or negative in a different quadrant. Then which ratio is positive or negative in each quadrant. That will help you solve these things, these kind of equations, right? So more complications coming, more confusion. So fun times. So make sure to specify where you're taking directions relative to when the question didn't really say exactly where these directions are relative to. They just say 18 degrees. 18 degrees to what? North, the vertical, the horizontal, northeast. Where is that direction being taken? That was given from the book. So these are poor questions. These are poorly phrased questions. When they don't give where the directions is being taken from, you could assume anything. So we assume relative to the horizontal, right? Is horizontal positive, up is vertical positive, right? On the horizontal true. Oh, so if these two forces are here, we say what AV and BV are, AH and BH are. And we had some mistakes here. This was, this 7 cos 115 is 2.96. Right, so a lot of these answers had to rework here. This is 0.11, right? So the resultant was velocity is still 7.27, but the angle is already 90.87. Now, the tangent at this negative number is a negative angle. We have to add 180 degrees to get a positive angle. And that quadrant theory, I think I need to explain that to you all, because solving trigonometric equations is not an easy thing. Like the inverse trigonometric ratio of a negative angle is a negative angle, but what positive angle that is, right? For instance, if you have to find say where's the display? Negative 0.5. Negative, right? If you have to find the sign of that. So it says second function, sine inverse of that. You say it give you a negative answer, negative 30 degrees. What is negative 30 degrees? What's negative angles? That's what we have to talk about next. This will be a challenge, right? But if I say 0.5, negative 0.5, if I do the cos inverse of that, you see is a positive angle. See the confusion? For sine, will give you a negative angle. For cosine, will give you a positive angle. 0.5 minus. If you do the tan inverse of that, you see again negative angle. What does a negative angle mean, and what you have to add it to in order to get the right answer? We might have to talk about that next. That is quadrant theory, where we talk about the different quadrants and what these angles mean in the different quadrants. Because a simple thing like solving this here, if it's negative, you could go on into problems, right? So this is the right answer here, but tan inverse and minus 66 is a negative angle. You had to add 180 to that to get a positive angle. But why had to add 180? Why not 270 or 360? So we'll talk about that next. So we originally wasn't really supposed to go through this chapter here. Originally, I said, chapter 23, you're kind of supposed to know it. So you're kind of supposed to go through 23, but not everything in chapter 23 you have to know. What we have to know is the graph of how these functions work. Now, this is a funny thing for you all. When you now see this, this is very confusing. You're accustomed with angles and a right angle triangle being less than 180 degrees. If you have a triangle, a right angle triangle, or any triangle, a matter of fact, every single angle is less than 180 degrees. So the idea of a sine of an angle and an angle crossing 180 degrees, this is kind of ridiculous to people at the first time, right? But centuries ago, people realized that they have to extend trigonometry to angles greater than 180 degrees. Remember, we defined the ratios in terms of a right angle triangle, right? If you see here, the original meaning of sine, cosine, and tangent is just ratios in a triangle. But that's really not what these things are. These things are functions. And as functions defined on a triangle in a particular coordinate system. So if you have a rectangular coordinate system like this here, you have 4 quadrants, okay? And what we do is, if you read here, you measure angles in an anti-clockwise direction from the positive x-axis. So the positive x-axis is this horizontal line, the right-hand side of the horizontal line, this right part here. See this A and X? That's the positive x-axis. We start measuring angles from that positive axis going in an anti-clockwise direction. So you know what anti-clockwise is going like that, right? Different from clockwise. So we label the quadrants in that way. Don't ask why, just learn it and accept this, right? Quadrant 1 is here, then 2, then 3, then 4. We counting in an anti-clockwise direction. We have 4 quadrants. Now our total circle is 360 degrees. So actually angle 0 is angle 360 degrees. The thing about trigonometry is we call these circular functions. When you look at these functions here, we call them circular functions. These are the functions that govern our circle work. Sine, cosine, and tangent is not really about triangles, and it's actually about circles. Right? Believe it or not. Circular motion traverses these curves here, sine, cosine, and tangent. Right? I have some nice YouTube videos. I'll show you these things to show you how all our mathematics connected. But if you draw a triangle here in one of the quadrants, given the angle, and you do trigonometry, we come up with certain ratios, the signs of the ratios. Where is cosine, tangent, sine, cosine, and tangent? Where are they positive and where are they negative? Right? So if you have a acute angle less than 90 degrees, right? Sine, cosine, and tangent is positive, right? The sine of an acute angle is positive, the cosine of an acute angle is positive, the tangent of an acute angle is positive. When the angle crosses 90 degrees, the triangle ends up in the second quadrant here. So the measurement of that angle is more than 90 degrees. So, I mean, it's kind of confusing, you know, to tell you that, okay, it have a triangle and the angle in the triangle is 150 degrees. It's like, what? How you just draw that, right? Well, this is how you draw it. You draw a quadrant and you measure 150 degrees from 0 in a clockwise direction. You come across any second quadrant here. That triangle in the second quadrant, if you notice, the vertical direction is positive, but the horizontal direction is negative. And the angle, the corresponding acute angle in the second quadrant is actually 180 degrees minus theta, where theta is the original angle. So in that second quadrant there, if you try to find sine is opposite over hypotenuse, right? That's positive because the opposite is the vertical direction and the hypotenuse is positive. So both of those positive things, the ratio is positive. But cosine of that angle now, cosine of any angle more than 90 degrees, it means that angle is in the second quadrant. The horizontal dimension, the adjacent, is actually negative. So cosine of an angle greater than 90 degrees but less than 180 degrees is actually negative. Okay? Same thing with tangent too. Once the adjacent takes part into it, the adjacent negative, so the ratio tangent is negative. Okay? So the only thing positive in the second quadrant is sine. So we see here, you know, they tell you, well, sine is positive in the second quadrant. In the third quadrant, if we do similar arguments, the only tangent is positive. And in the fourth quadrant, only cosine is positive. Everybody's positive in the first quadrant, right? So we see here the reading here, they show you how the ratios change signs as the angles increase. Okay, and there's a mnemonic to remember this, all silly tomcats, all silly tomcats is one mnemonic, right? Going in an anti-clockwise direction to tell you in which quadrant, which ratio is positive. So in third quadrant here, these are angles greater than 200, greater than 180, but less than 270. Is greater than a half turn, but less than a 3/4 turn. Angles in this region here, if you find the sine of them, the sine is negative. If you find the cosine is negative, but if you find the tangent is actually positive. I could try that, right? Try it with a calculator. In the second quadrant here, an angle is like angle in the second quadrant is 150 degrees. If you type 150 and you find the sine of that, you see it's positive. But 150, the cosine is negative, and 150, the tangent is negative. And that's because the angle is in the second quadrant where only sine is positive. So the value of an angle could be anything, you know. We normally think of angles between 0 and 360 degrees, but no, I could ask you, what is the sine of 945 degrees? I could ask you that. 945 was the sine of that angle. It have a value. These are intelligent questions. Might make sense to you, but that's where the circular motion comes in. That's why it's called circular functions. These functions, the domain is typically between 0 and 360 because this is the full value of the function. This is called a sine wave here. But that wave oscillates, right? It repeats. So after 360 degrees, between 360 and 720, it repeats again like that. There's a repeating curve, right? It's very different from the functions you're all familiar with, like e to the x and ln x and x squared and all them polynomials. None of those things circular, none of those things repeating. This is the importance of the trigonometric functions in mathematics and in engineering. Engineering is filled with repeating processes, things that repeat themselves. In an electrical circuit, you have electrical oscillations. In a mechanical system like a bridge or a pendulum, you have mechanical oscillations, right? In the weather, you have biometric oscillations, right? All these systems, economic systems have oscillations, financial systems, biological systems, electrical systems, mechanical systems, thermodynamic systems, fluid systems, all these things have oscillations. And the functions that govern oscillations in mathematics is sine and cosine. That's why they're so important. These curves, the domain, they typically give 0 to 360, but that x-axis, it goes on forever, yeah, just like any other function. But the function doesn't keep on growing. It actually repeats. It stops at a while, for a while, and then it comes back again. Like the graph of sine A, when you look at here, that curve just repeating, you know, between 1 and -1. It don't ever cross +1 up here, and it don't ever cross -1 down here. It keeps repeating itself. So if I want to find 945, I want to find the sine of 945. But what does this map to exactly? I could just keep subtracting 360 from it to get it back to the original domain, right? Then minus an x 360. So we have an angle now that is less than 360. Which quadrant this angle is in? 225 is more than 180 degrees, right? So that means it's in the third quadrant. And in the third quadrant, only tangent is positive. What is the principal value of that angle? It is the angle minus 180 degrees. So you minus 180 degrees from this because it's in the third quadrant to get 45 degrees. That's 45, that's this angle here, theta 3, right? So then the sine of 945 degrees is the same as the sine of 45 degrees, but negative. Sine of 45 is positive 7.07, right? I will find the sine of this here. So then the sine of 225 is per negative sine on that. And that's what we got, 945 The sine of that was negative. So you see how it oscillates, it repeats itself. Say you wanted to find an angle of, we want to find the tangent of, say, 750 degrees, right? You want to find the sine of this. It's not the sine, the tangent, right? Okay, 750 degrees, let's convert it to an angle less than 360 degrees. So let's subtract a 360. 390, right? Let's subtract our next 360 because that's bigger. So that's 30 degrees. The tangent of 30 degrees, right, is a positive value. So the tangent of 750 degrees, I expect it to be a positive value. See, positive. So that's the easy part, finding the ratio, finding the value, not just the value, the sign of a ratio, okay? So sine, cosine, tangents, those are ratios. And when you want to find if it's positive or negative, it's easy, calculator will tell you. But how you go the other way around? Like say you do an equation and you want to solve some equation. Say you want to solve, I don't know, say I have some equation, sine x equals negative 0.85, right? Which angle has a sine that's negative 0.85? Well, first of all, sine of some angle is negative. Where could that angle be? Sine is positive in the first quadrant and the second quadrant. So that angle had to be somewhere down here. So as a big angle. But they need to give you a domain. There's usually say, they'll say something like solve they'll say solve this equation here. For say so tell you x is some angle between 0 and 360 degrees. Solve this equation here for x. The fact that it's negative means that x had to be somewhere down here in the third quadrant or the fourth quadrant. So it had to be an angle more than 180 degrees, but less than 360 degrees. So what you have to do, for each quadrant, you have to find what the principal value is. For the third quadrant, the principal value, you see there use some examples here. That angle crosses, it's always the principal value angle is always the angle between the hypotenuse and the horizontal. So if you cross 180 degrees, that angle is say the angle is in the third quadrant here for tangent. The value of the angle between the hypotenuse, which is like this straight line here, this line here, AO. That's theta 3, right? It's always the angle between the hypotenuse and the horizontal. So that line, you really need to subtract 180 degrees from that angle. Now we don't know what the angle is. So what we need to do, we need to solve sine x is 0.85. Now, if it put this raw in your calculator, let's see what we get. 0.85 negative, and we do second function, we find the sine of that. it's gonna give you a negative angle, but that you can't put that as an answer. X can't be negative. X is an angle from 0 to 360 degrees. What the calculator give you can't use, right? So what you have to do is solve the equation for when it's positive, right? So let me show you what you do. First, you solve this equation here, where it's positive, right? So we say sine x is equal to 0.85. What does this give here? Sorry, we call it y, right? If sine y is 0.85, that means y is equal to so we find the sine inverse at the positive angle because we want the principal value, right? So we say 0.85 and second function sine. This is 58.21 degrees. So we call this 58.21 degrees, right? Now y is the value in the first quadrant, okay? But this negative 0.85 here is the same ratio, but just a different sign. This means we take this angle 58.21 degrees and we use that principal value to find an angle in the third quadrant and an angle in the fourth quadrant. For it to be in the third quadrant, that angle is theta 3. That is an 58.21 degrees. That is theta 3. That's the angle underneath the horizontal. So then the third quadrant angle for this domain here is 180 degrees plus that. Okay. So if y is the principal value in the first quadrant, principal value is the angle in the first quadrant that has this positive ratio. Okay. What angle has a positive ratio? Sine inverse of 0.85. We say 58.21. So if y is 58.21, y is the angle in the first quadrant here. To find the angle in the third quadrant, you just need to add that theta to 180 degrees. So the angle in the third quadrant is plus y. If we add 180 degrees, add 180. This is an angle in the third quadrant, 238.211, right? So 238.21. This is an angle in the third quadrant. Well, what is that? This angle here, if I try to find the sine of that, you'll see what I got? Negative 0.85. That's the original solution here. Basically, calculator wasn't giving you that answer. Calculator was giving you a negative answer. We can't We can't use that negative answer here. We have to convert that negative answer, which, by the way, a negative answer is an angle in the fourth quadrant if it's a negative acute angle. This negative acute angle here that I was getting is negative 58. Negative angles are measured clockwise. So if you measure clockwise, you see it's negative, but anti-clockwise is positive. That is the convention. So negative 58.21, this is a acute angle, 58, because it's less than 90. But it's in the fourth quadrant, because if I go clockwise and I measure 58.2 degrees, I will still be in the fourth quadrant. So the calculator giving you a negative answer, but a fourth quadrant answer. To find the actual value in the fourth quadrant, if you know it's a acute angle in the fourth quadrant, you just, add 360 degrees to this negative value here. So if you add 360, this is the fourth quadrant, it's 301.79, right? So, and then in fourth quadrant, it's 360 minus y. That is 301.79. Okay. Again, the calculator didn't give us this answer. We work out this answer, right? But if I find a sign of that, look, it's negative 0.85. Okay. You had to know which quadrant the angle is in. And you have to give an answer based on the domain that they tell you the answer is in. I cannot give negative answers for this problem because they say x is between 0 and 360. I have to give positive angles. If I know angle is negative and it's in the fourth quadrant, then I just need to add 360 to that negative value or subtract it from 360, which is what this is here. Y is the positive angle in the first quadrant, so I subtracted from 360 to get this value. These two values here will never be given by a calculator. But when we put it in the calculator, we see negative 0.85 is what we get, which is the original question they give us. What the calculator was giving us was negative 58.21, which we can't use directly. We have to use that indirectly. The principal value is the positive angle in the first quadrant that gives a positive ratio. Okay, so the principal value is the angle in the first quadrant that gives a positive ratio, right? So when I give you a trigonometric equation to solve, and this value here is negative, you take this positive value and you're trying to find that value in the first quadrant, and that's your principal value. Then you take that principal value now, and you might have to subtract it from 180 degrees to get an angle in the second quadrant. You might have to add 180 degrees to get a third quadrant angle. But you have to subtract it from 360 to get a fourth quadrant angle. Why you're doing these things is because the secondary value is the principal value, right? The secondary value is the value in the quadrant where you add the principal value to something where you subtract it from something. The point is the principal value is the angle it makes with the horizontal. So you see theta 1 here is with the horizontal, theta 2 is the horizontal, theta 3, theta 4. These are all angles with the horizontal. So if your horizontal is a certain value, to get an angle in the second quadrant is 180, I have to minus the angle from 180. To get in the third quadrant, you obviously had to add 180 to the angle, right? And to get in the fourth quadrant, you just subtract the angle from 360. That's the idea what we're doing here to solve these kinds of equations. The bottom line is your calculator not always going to give you the answer you need directly. You might have to take that answer and change it around. You have to study this chapter here. What page is this? 200. You have to study these examples here and read the discussion here to what they're talking about. When they give you a question, you have to figure out which quadrant it's in, right? So we could do an example here. What's the example? So again, between 0 and 360 degrees, the sine of an angle is negative 4.38. The fact that sine negative, that means is in the third and fourth quadrant. 468 point, oops, 0.4638 negative, right? If you find the inverse sine of that, it's going to give you a negative angle. But you can't use that because they want all the angles between 0 and 360 degrees. They want positive values for that. But this is the principal value here. Watch what it will do. You see 27.63, right? See here, 27 point sine inverse. I'll take the positive ratio, right? To take the positive value, which is positive 0.4683. Find the sine inverse of that. You'll get a acute angle in the first quadrant. If that's our first quadrant angle, right? The negative sign is in the third and the fourth quadrant. So you see here, to get angle in the third quadrant, you have to come here and go all the way past 180 and then add that angle theta here to 180. To get angle in the fourth quadrant, remember it's always the angle is with the horizontal. You have to start from 0, go all the way around here and come to this angle here. So you're essentially subtracting the angle from 360. So you add 180 to the angle, and then you subtract it from 360 to get this angle. That's what we did here. We add 180 or we take it away from 360 to get that. Sine of a negative value. Sorry, sine being a negative value for a question like this where you want positive answers between 0 and 360. That's a third and fourth quadrant answer. That's what they give you here. Now, when you plug in these values in the calculator, you will get the ratio negative 0.4638. But that's not the value the calculator was giving you. Calculator will never give you these values here. 20763 and 332.37, right? So this is where human intervention comes in. The calculator gives you the principal value, i.e. the value in the first quadrant, or the value in the fourth quadrant. Usually that's what I give. It's up to you, the human, to figure out how to use that value to solve the equation. So we see here, the moral of the story is solving things like this here, sine x is negative 0.85, is actually not very straightforward. You have some theory how to learn, and that's what this section of the book teaches you how to do. What is it? 23.2. Any magnitude angle, okay? And they could mix it up, you know. They could mix it up and give you a value. Like if you had to solve this equation here in a different set of values, input values allowed, then the answer is going to be different. So you could do this question here, same thing, right? We duplicate this question here, but they give you a different domain. They say they want an answer between negative 180 degrees and 0. So x had to be between negative 180 degrees and 0. Then your answer is different here. Because now they want negative values. They want, look at the lower bound, negative 180 degrees, but the upper bound is 0. Right? So you can't give them a positive answer. Now here, when you use the calculator, right? What we had? 0.85, right? 0.85 minus, oops. 0.85 minus second function sine inverse. Now this negative value, now we could use it because this is a fourth quadrant angle. A negative angle, a negative acute angle is an angle in the fourth quadrant, right? Less than 90 degrees, the magnitude is less than 90 degrees, but it's negative, so it's clockwise. So that's a fourth quadrant angle. But we know that's a legit angle, okay? But we could do the same thing. We could say the same thing, right? Here, I could come now and say, down here, we know it's in the third quadrant and the fourth quadrant. However, for this domain here, a fourth quadrant angle is 3. You wouldn't need to subtract it from anything. You just measure in an anti-clockwise direction. So the fourth quadrant angle is just negative y, right? So it's just negative that. And that's the answer. Because an acute angle in the fourth quadrant, just measure it anti-clockwise. The third quadrant, now we're measuring anti-clockwise. Anti-clockwise is positive, we're measuring clockwise, right? So fourth quadrant, we measure clockwise, so we go negative. For a third quadrant, with this domain here, you have to go clockwise. It's negative angles they're talking about. So if you look at the diagram here that they drew, this T here, I need to start from 0 and go in a clockwise direction to reach T. So that's a negative direction. Now, ordinarily, I would go negative 180 degrees, and then you have to add the principal value. So that's what we do here in the fourth quadrant. We add the principal value to negative 180 degrees. So negative 80 plus 58.21. So we change the sign here, and we subtract 180 degrees. 121.79. Okay, that's the third quadrant angle. Now, if you come here and you find the sign of that, you see, negative 0.85. So we know this answer, right? But it's not the answer a calculator will ever give you. Again, you have to figure out that answer the calculator gives you. You have to figure out how to use that. Okay? So the same problem, when you solve it for different domains, you get different answers. But the answers you get, to get them, you have to interpret it with a diagram. You do some geometry for where that angle is located. For this one up here, it was positive angles. But this one down here, it was negative angles. So it depends not only on the ratio to tell you whether it's positive or negative. It depends not only on the actual ratio, if it's sine, cosine, or tangent. It depends on the trig function. It depends on the domain. So it depends on 3 things: the ratio, the value, the trig function, and the domain. You have to take these 3 things into account. So you kind of need to draw a diagram for these problems when you have to find the inverse sine or cosine or tangent of a value. It is not very easy. And these diagrams and these parts of the textbook show that these things are not easy for you, right? So go through this again and make sure you understand it. But we kind of moving on from this here. This is precursor to solving problems like this here. Because you're gonna have in vectors, you're gonna have to find arctan, arcsine, arccos, and negative values. What does that mean? This value here, negative 66.09. When you find the tan inverse, they give you a negative value. But negative value don't make sense. So look at this diagram here. Where's a negative angle? That's an angle going in the reverse direction. That's not what we need. We need an angle going in the positive direction. Tangent is negative in the second and the fourth quadrant. we can't use a fourth quadrant angle, so we had to use a second quadrant angle. A fourth quadrant angle is a big angle. Look at the diagram here, fourth quadrant angle don't make sense. A second quadrant angle is what makes sense. And that's why we get this answer 90.87. This is less than the 1 degree. It's less than 1 degree more than the maximum first quadrant angle, which is 90 degrees. This is where the diagrams help you. The diagrams help you figure out where that angle is and how to use the value given by the calculator to find the angle. It's not very easy. Hope you all understand that.